Welcome to the first lecture of our physics lecture series. In this lecture, we're going to go over some basic foundations and fundamentals of physics. The first and foremost thing we have to remember are our measurements, and they will vary. You need to understand what units correspond for which quantities. Also, you have to know the prefixes and the scientific notations for certain measurements. So, if you remember the old adage, King Henry doesn't mind drinking chocolate milk, that'll get you from kilo to milli. However, you generally need to know the smaller measurements and sometimes the larger ones for the MCAT. Before we begin, let's go over the difference between scalar quantities and vector quantities. Scalars have only magnitude, and examples are distance, speed, energy, and pressure. Vectors, on the other hand, have both a magnitude and a direction. Examples are displacement, velocity, and acceleration. These are all different, so when you're thinking about which quantity you're calculating for, make sure you have a good idea whether or not they're a scalar or a vector. When discussing vectors in particular, there are times we have to manipulate them or modify them. The first one we're going to go into is vector addition. This is done through the tip-to-tail method. So if I were to have two vectors, like so, A and B, the resulting vector will be placed here, A plus B, tip to tail. This can be comprised of more than two. So if I were to have three vectors, like this, A, B, and C, the resultant vector would be placed here, A plus B plus C. At times, we will have to split vectors into components. This is especially true if we are dealing with two-dimensional systems, where we need a horizontal and a vertical component. Vectors won't always travel along pure horizontals or pure verticals, or there may be times we have to adjust them accordingly. To do this, we use trig relations, or SOHCAHTOA. Sine, opposite over hypotenuse, COH, adjacent over hypotenuse, and TOA, opposite over adjacent. If I were to draw a right triangle out with an angle theta and our vector, we could break it down into a horizontal and a vertical component. To get the horizontal component, we would use our vector and the cosine of the angle. The horizontal component is done in much the same way, except we use sine instead of cosine. If we were to have a horizontal and a vertical component, but not know the vector itself, we could use the Pythagorean theorem. This can also be used to calculate any of the three. So if we need a vertical component or horizontal component or the vector itself, so long as we have a couple other values, we can still solve for it. If we remember what the Pythagorean theorem is, it's simply thus. It states that a squared plus b squared equals c squared for a right triangle. In terms of physics, if we were to deal with a vector v and a horizontal and a vertical component, so if we were to call this y, we were to call this x, the resulting vector would be the square root of the horizontal component and the vertical component, like thus. What if we wanted to figure out the angle? Generally, we would use the tangent function, which, if you remember, TOA is opposite over adjacent. Bear in mind, if we use inverse trig functions, we can figure out that angle. Finding the resultant. This is kind of like vector addition. However, it's when we're adding two vectors and looking at the components of the two, instead of taking two separate vectors and seeing where it ends up. If I were to have two vectors, let's say v1 with its horizontal and its vertical component, and v2 with their respective components, and I wanted to find a resultant vector, r, it would be the sum of v1 and v2, like so, if they were superimposed on each other, that is. Do note that their vertical and their horizontal components are also additive. We've kind of covered adding vectors together, but what if you have to subtract them? You're basically adding vectors with equal but opposite direction. So if I were to take a minus vector b, it would be the same as a plus negative b. Seems a little odd, but let's see an example. If I were to have vector u and vector v, the subtracted vector would be here. Pretty straightforward, right? What if they were pointing in very different directions, though? Where would the subtracted vector go? Well, right down the middle. So it would be something like this. Bear this in mind when you're manipulating vectors. You need to know whether or not you need to add them or subtract them. What if we were to take a vector and multiply it by a scalar? Personally, I think this is the easiest manipulation, since scalars are only magnitude. If I were to have a resulting vector from a scalar multiplied by a vector, it would simply take the magnitude of the scalar and multiply it to the vector itself. So if I had vector A multiplied by some scalar n, this would result in vector B. Where it gets tricky is when we're talking about multiplying vectors by other vectors. There are two ways to do this. One is through the dot product, which is to generate scalar quantities like work. You take the two vectors and you multiply it by cosine theta, which is the angle in between. So if I were to have a vector A and a vector B, I'd be looking at the theta in between. The cross product, on the other hand, generates a third vector, like torque. You do this the same as for a dot product, however, you would use sine theta instead. Also, you need to use the right-hand rule to determine direction. The right-hand rule for vectors is a little different than the one you're going to use for electricity and magnetism, but make sure you keep the two straight. For the right-hand rule with vectors, you take your vector A and line it up with your index finger. Then take your palm and line it up with vector B. Whatever your thumb is pointing to is where the A cross B vector would be pointing. Do note that on the MCAT, you're dealing with a two-dimensional screen. There is the possibility that the vector that results from the cross product is going to point into or out of the page. If it points into the page, it'll generally be marked by a circle with an X on it. And if it's pointing out of the page, it'll be marked with a dot, like so. So it'll either be floating into the page or out of the page. Make sure you know these distinctions while you're on test day. The next little bit of our introduction to physics, we'll talk about some other fundamentals. The first is force. This is a vector quantity that represents pushing or pulling on an object. The SI unit for this is the Newton. The one in particular that we're going to focus on right now is gravity, which is the attractive force felt by all matter, and the respective gravitational force, the equation for which is listed below. When we get into electricity and magnetism, you will notice that electrical force has a very similar equation. It might be helpful for you to study them together, just so that you don't have to remember as many equations. Next subject we're going to go into is mass and weight. Make sure you know the distinction between these two. This is something that a lot of students get confused. Mass is a measure of a body's inertia, or the amount of matter in an object. Note it's a scalar quantity. Weight, on the other hand, is the measure of gravitational force on an object's mass. This is a vector quantity. Notice the distinction. This is not the same as mass. The equation for weight is F equals mg, with g being the acceleration due to gravity. On Earth, it's 9.8 meters per second squared. However, on other planets or in other environments, that gravitational acceleration might be less or more. An example would be, so if I were to say I was floating in space, I could say I am weightless. However, at no point would I ever be massless. Our final topic for the day is Newton's laws. Sir Isaac Newton is largely considered the father of modern physics. So these three laws generally govern most principles. The first law is inertia. It states that matter tends to resist change. A body either at rest or in motion with a constant velocity will remain so unless acted upon by a force. So, long story short, whatever you're doing at that current moment, you're going to tend to want to stay in that. If you're resting, you want to stay there. If you're moving, you're going to want to stay moving. The second law is force. It states that an object of a mass m will accelerate with the vector sum of the force results in a non-zero resultant force vector. Force equals mass times acceleration. So when you're looking at the force of an object, you have to look at how fast it's moving and its mass. The last law is the action and reaction. Simply put, it states that every action has an equal but opposite reaction. An example would be as if I were to push against the wall. While I am exerting a force on the wall is exerting a force on my hand equal to what I am pushing against. So, basically saying, for every single force, there has to be something that counteracts. This is a very important principle when we're talking about free body diagrams, which are something that we'll go into in the next lecture. Alright, so that'll do it for our discussion of physics fundamentals and foundations. In the next lecture, we'll go into some applications of these foundations. Join us then.